Hello, this is the lecture for Combinatorics class on section 8.2, exponential generating functions. So I'll be talking about the subsections on starting from a recurrence relations and finding the exponential generating functions, and then using those to compute a closed formula. So before we have been talking about finding ordinary generating function for a starting from recurrence relations. So sometimes that is not possible, but it's possible to find what's called the exponential generating function. So if we look at this example, this is a sequence where we're given the recurrence relation. So we will find the closed formula for this sequence using the exponential generating function. So given a sequence of numbers, we can define a formal power series where we have x to the n divided by n factorial times a coefficient, and then take the sum over all n. So this power series is called the exponential generating function of this sequence. And the reason this is called exponential is because of the fact that if we have the constant sequence that's always 1, 1, 1, 1, 1, the generating function, the exponential generating function for that would be e to the x. All right, so this is from the book, so I'll explain this in more details. So again, we have, we're given the initial value, a0 is 1, and then we're given this recurrence relation. And first we will find the exponential generating function, and then we'll use that to find a closed formula for a sub n. So first define capital A of x to be the exponential generating function. Of the sequence a sub n. So now I'm starting with the recursive formula that is given. And then I multiply both sides by x to the n plus 1 over n plus 1 factorial. And the reason I choose this, I could have done it differently, but I was trying to match the index of the left-hand side. All right, and then like we've done in the past for ordinary generating function, I will take the sum over all n, and then I want to do some simplification here, so I cancel out like the n plus 1, and then after you simplify, you would get this, and I have marked this with a star because we will use this later. So now if you look at the left hand side, that's really the same as the exponential generating function, but we're missing the first term a sub 0. So the left hand side is equal to capital A minus a sub 0, which is 1. And now if you look at the right-hand side, so the first term of the right-hand side is this one. So I'll just take out the x to match the indices, and that will give me x times capital A. And then if we look at the second term of the right-hand side, that's that one minus, including a minus sign. So I have that. So now I will separate the n and minus 1. So I get this, and then I will So I will then change the index here to 1 because the first term here, if we're starting at 0, if when n is equal to 0, the whole term just becomes 0, so it's fine to change the starting index to 1. And then I take out the x for the second term, and now I simplify. I cancel out the n to get this part, and then the second part is still the same. And now I want both of the terms to start at the same value, so I want the index to be the same. So now I will change this back to 0, starting at 0. So the n plus 1 becomes n plus 2, and then n minus 1 becomes n. And the second part is still the same. And now I will move the x squared out. And now what I have, because this part and this part are both equal to e to the x, I have this. Okay, so now I put together everything that I need. So back to the star equation. So we've already computed this left-hand side and also the right-hand side. So the left-hand side of star is capital A minus 1. And then the first part of the right-hand side we've already computed to be this one. And then the second part of the right-hand side is that. So from here, I can then solve for capital A. So I just move the terms that have A to the left-hand side. And then I move the terms that don't have A to the right-hand side. So I get A times 1 minus x. And I have this. So then I divide both sides by 1 minus x. And if I do more simplification, I will get 1 over 1 minus x plus x e to the x. So this is the answer of part 1. This is the exponential generating function for the sequence a sub n. Alright, so now we want to find a closed formula for the sequence, and we will use the exponential generating function. So this is the exponential generating function, and now I want to turn this back into a power series. So the first part is just the geometric series, and then the second part is x times e to the x, but we know how to compute the power series for e to the x. And now I will bring the x inside. And then now what I want really is that I want something that looks like x to the n divided by n factorial, because that would be the what we need for the exponential generating function. So that is the reason why I changed the index to start at 1 here, so I can write x to the n. And also I want this to, like, I want both parts to match. Alright, so in this step, I want to rewrite what I have in such a way that I have x to the n over n factorial as a factor. So in the first part, I just multiply by n factorial over n factorial. And then for the second part, I multiply by n over n. And in this part, I changed the starting index again to start at 0 because I want the first and second part to be the same. And now this equality holds because 0 times anything is 0. And now I can combine the two summation into one summation. So I have n factorial plus n times x to the n over n factorial. So since the coefficient of x to the n over n factorial in my capital A function is n factorial plus n, we have that the closed formula for the sequence must be n factorial plus n. So this is the end of example 8.17. For part of your reading homework, I want you to read the second example in this section. So again, you're given recurrence relations, and you're asked to find an explicit formula for f sub n. And again, in this situation, it wouldn't be possible to find the ordinary generating function, but you could find the exponential generating function. So the book gives a quick explanation to find the answer. What I want you to do is explain the computation in details, just as I have done for the previous example. So to go from here, you would first need to do partial fraction decomposition to find that. And then there are a few extra steps to get to the solution.